hello everyone. This is P. Mabu Hussain, Assistant Professor in EEE, Institute of Aeronautical Engineering, Hyderabad. So today in this video, we are going to discuss about the inductance of single phase two-wire line. So this topic comes under the module 1 of electrical power transmission systems. So let us consider a single phase transmission line. A single phase transmission line will be having the two conductors, right? Let it be 1 and 2. So 1 and 2 are the two conductors of a single phase transmission line, and let us assume that this conductor 1 is carrying a current I1 and conductor 2 is carrying current I2, and also assume that the radius of your conductor 1 is R1 and radius of conductor 2 is R2. And distance between the two conductors from center to center, you have to assume it to be capital T. Okay, so now if you observe the figure here, so from center of the conductor 1 to the surface of the conductor here, so the distance will be D minus R2, and from the center of the conductor 1 to the surface of the conductor at this place, so this will be D plus R2. Okay, so now if the conductor 1 carries the current I1, it produces the magnetic flux around it. Okay, so the magnetic flux are concentric circles and they will be distributed like this in the figure. Okay, so let us consider the flux linkages of circuit 1, caused by the current flowing in the conductor 1 only. Okay, so first initially we are assuming that the flux linkages of the circuit will be caused by only the current flowing in conductor 1. Right, in such a case you need to make some observations in this regard. The first one is that the external flux from R1 to D minus R2, if you observe, right? So from R1 to D minus R2 up to this, right? If you observe the external flux of conductor 1 from R1 to D minus R2, so this flux links all the current flowing in the conductor 1, so which is I1. And the second observation is that, so if you observe the external flux from D minus R2 to D plus R2. So that means from D minus R2 to D plus R2, from here to here. Okay, so if you observe the external flux linkages from D minus R2 at this location to D plus R2 at this location, then this external flux links a current whose magnitude is progressively reduces to 0 along this distance. Okay, as you are moving the flux linkages from D minus R2 to D plus R2, so in such a case these flux linkages, this external flux links the current which is progressively reducing to 0 as you are moving from D minus R2 to D plus R2. So why? Because this happens because of the effect of negative current which is flowing in the conductor 2. Okay, and the third observation you have to see here is the, so B and D plus R2, the flux links with the current will be 0. Okay, so B and D plus R2, so right, so from here to this side, okay, from D plus R2 to some distance here. Okay, so the B and D plus R2, the flux links a net current of 0. Okay, these observation you have to make here. Okay, so if you see again, if a current is passed through conductor 1, magnetic flux will be developed. That magnetic flux lines are concentric circles and they will be distributing like this. Okay, now if you consider only the current flowing in the conductor 1 and if you consider only the flux of conductor 1 alone, so then you can make 3 observations here. So first observation is that this external flux, so external flux of conductor 1, so from R1 to D minus R2, from here to here, so this external flux links a current whose magnitude links all the current which is flowing in the conductor 1. And if you second observation is that from D minus R2 to D plus R2, this flux links with the current will progressively decreases to 0 as you are moving from D minus R2 to D plus R2. So this decrease will be happen because of the current flowing in the conductor 2. Now if you observe B and D plus R2 distance, so then the net current linked by this flux will be 0. Now you need to calculate the inductance for this transmission line system. Okay. Now for calculating the inductance due to current flowing the conductor 1 alone, you have to make some simplifying assumptions, right? So that simplifying assumption is that if D, so the capital D here is nothing but distance between the two conductors from center to center, this distance. Okay. So now if this distance between the two conductors is much greater than the radius of conductor R1 and radius of conductor 2, right? So if D is much greater than R1 and R2, so generally it is the case for a overhead transmission line. It can be assumed that the flux from D minus R2 to the center of the conductor 2. So the flux from D minus R2 to the center of the conductor 2. So that means we are taking from here to here. Okay. So the flux from D minus R2 to the center of the conductor 2 links all the current I1. So the flux here in between links all the current I1, and the flux from center of the conductor 2 to D plus R2 links the zero current. So right. So from here to here D plus R2. So here this flux between this center of the conductor to D plus R2 will links the zero current. So this assumption you have to make. Okay. So then based on the above assumptions, the flux linkages of the circuit caused by the current flowing in the conductor 1, we can write it as lambda 1. So this lambda 1 is equal to 2 into 10 power minus 7 I1 ln D by R1 dash. Okay. So this lambda 1 is the flux linkages of the circuit due to current flowing in the conductor 1 alone. So here you are taking current flowing through the conductor will be I1. Okay. So the total flux linkages equation you can write it as lambda 1 is equal to 2 into 10 power minus 7 I1 ln D by R1 dash. So now let it be equation 1. Okay. So this equation you got by considering the current flowing in the conductor 1 alone. Okay. And by making some simplifying assumptions also. Right. In a similar way, you can calculate the inductance. Once you know the flux linkages lambda, so then you can calculate the inductance L. Okay. The inductance L is equal to lambda by I. Right. Here, so the inductance of conductor 1, you can write it as L1. So then in such a case, flux linkages caused by current flowing in the conductor 1 by current flowing in the conductor 1. Right. So now this lambda 1 here from the previous equation, this is 2 into 10 power minus 7 I1 ln D by R1 dash. Right. That if you write here, so 2 into 10 power minus 7 I1 ln D by R1 dash by this I1. So I1 will get cancelled. So the inductance of conductor 1 which is L1 will be equal to 2 into 10 power minus 7 ln D by R1 dash you will get. Right. So this we are writing here. Okay. L1 is equal to 2 into 10 power minus 7 ln D by R1 dash. Let it be equation number 2. Okay. So we calculated the flux linkages of conductor 1 by considering the current flowing in the conductor 1 and the inductance of the conductor 1. So similarly, you can even find out the flux linkages and inductance of conductor 2 also. So if you consider the current flowing in the conductor 2 alone, so then the flux linkages of the circuit, so which is flux linkages of the circuit caused by current flowing in the conductor 2, you can written it as a lambda 2. Okay. So the flux linkages of the circuit due to current flowing in the conductor 2, so which is lambda 2 will be equal to 2 into 10 power minus 7 I2 ln D by R2 dash. Right. While deriving this equation, you have to take some assumption which you have taken while calculating the flux linkages of your conductor 1. So same assumptions if you consider, so you will get the same equation similar to that. Okay. So once you know the flux linkages of conductor 2, you can find the inductance of conductor 2 also. Right. The inductance of conductor due to the current flowing in the conductor 2 only, so will be equal to L2. So that L2 is 2 into 10 power minus 7 ln D by R1 R2 dash here. Okay. How you got this equation? From equation 3. So you know the flux linkages. So then inductance of conductor 2 will be equal to flux linkages of conductor 2 by current flowing in the conductor 2. Now if you substitute lambda 2 here, so then you will get the L2, which is the inductance of conductor 2. So that value will be equal to 2 into 10 power minus 7 ln d by R2 dash. Okay, so this is how you can determine the inductance of single conductor 1 and single conductor 2 in a single phase transmission line system, right? So now if you consider the total transmission line system, if the two currents, if you consider, okay, if the current I1 is passing through the conductor 1 and current I2 is passing through the conductor 2, in such a case, the total inductance of the circuit, you can write it as L. So that the total inductance of the circuit or loop, you can say, so that will be equal to L cap. So that L is summation of L1 and L2. So here L1 is the inductance of conductor 1 due to current flowing in the conductor 1 only, and L2 is the inductance of conductor 2 when current flowing in the inductor 2 alone. Now if both currents, if you consider, so you will get the total inductance of the circuit. The total inductance of the circuit is the summation of two inductance L1 and L2. Okay, now already you know what is this L1. So L is equal to L1 plus L2 here. So now from L1, so L1 will be from the equation 2, you can write it as 2 into 10 power minus 7 ln d by R1 dash. So this will be 2 into 10 power minus 7 ln d by R1 dash. Okay, and L2 will be, so 2 into 10 power minus 7 ln d by R2 dash. Okay, so now in the both terms, so 2 into 10 power minus 7, you can take it as common. So then if you take 2 into 10 power minus 7 as common, so then you will get ln d by R1 dash plus ln d by R2 dash. Right, this ln d by R1 dash and R1 dash plus the ln d by R2 dash, you can write it as ln d square by R1 dash into R2 dash. Okay, so 2 into 10 power minus 7 ln d square into R1 dash by R2 dash whole square. So this even you can write it as, so 2 into 10 power minus 7 ln d by R1 dash R2 dash whole root whole square you will get. Okay, so this is the total inductance L. So from the Quiz equation you can write L is equal to 2 into 10 power minus 7 ln d by underscore root R1 dash R2 dash. So from this you will get the final equation as 4 into 10 power minus 7 ln d by underscore root R1 dash into R2 dash. Right. So this is the units for inductance are henries per meter. Okay, here we are considering only the 1 meter length of the conductor. So the units are henries per meter. Okay, so you got the inductance of the total circuit by considering current flowing in conductor 1 and conductor 2 both, right? So now if the radius of the two conductors are the same, right? If R1 dash is equal to R2 dash, so let it be equal to R dash. In such a case, what will be the inductance for equation? So then this equation can be modified as L is equal to 4 into 10 power minus 7 ln d by R1 dash and R2 dash both are equal. In such a case, you will get R dash whole square. Okay, so in place of R1 dash and R2 dash, we are going to substitute R dash. Okay, in such a case, this product R1 dash and R2 dash, that product will become R1 dash whole square, and this is having square root. So now this square root and this will gets cancelled. Okay, so the inductance will become now to be equal to 4 into 10 power minus 7 ln d by R dash. Okay, so this is the total inductance of the single phase two-way transmission line when the radius of two conductors are the same. Okay, so when radius of two conductors are the same, this is the expression. Okay, so if the radius of two conductors are not same, you have to use this expression. Okay, so now this inductance will be generally represented in henries per meter. Okay, so now if you convert the ln term into logarithmic terms, okay, here you have the ln term, right? So this ln term you can convert into logarithmic term. So that means base to the 10. Okay, so then in such a case you will get the inductance value will be equal to 0.921 log d by r dash base 10. Here the units will become millihenries per kilometer. Okay, how you can convert this? How you can convert this ln d by r dash to log base to the base 10? See here. How you can write this is L is equal to 4 into 10 power minus 7. Okay, here ln is nothing but log d by r dash whole to the power of base c. So ln is nothing but whole to the power of base c. Now here this log this ln you can convert into base 10 like this, log d by r dash to the base 10 multiplied by log 10 to the base e. Okay, so here we have 4 into 10 power minus 7. Okay, so this is in henries per meter. Now if you calculate the product of these two and convert the millihenries into henries per meter into millihenries per kilometer, so then what you will get here? So this will be 4 into 10 power minus 7 ln d by r dash to the base 10 log 10 to the base e. When you convert henries per meters into millihenries per kilometer, you have to multiply this total with 10 power 6. Okay, in such a case, the final value if you calculate, so then you will get this equation. Okay, L is equal to 0.921 log d by r dash to the base 10 millihenries per kilometer. Okay, so this is how you can determine the inductance of a single phase transmission line system. Okay, so you can use either this equation or you can use this equation if the radius of two conductors are same. So the next one is inductance spacing factor or inductive reactance spacing factor. What is this inductive reactance spacing factor or inductive spacing factor? So let us see, right? So now from equation number 2 here, so you know the inductance of conductor 1, which is L1 is equal to 2 into 10 power minus 7 ln d by r1 dash. In similar way, from equation number 4, L2 is equal to 2 into 10 power minus 7 ln d by r2 dash. So we are going to take those two equations here, right? L1 is 2 into 10 power minus 7 ln d by r1 dash, right? So now this equation you can write it as L1 is equal to 2 into 10 power minus 7 ln 1 by r dash plus 2 into 10 power minus 7 ln d by 1. Like this you can write. Okay, so here this ln term we are going to write it as ln 1 by r1 dash plus ln d by 1, like that. Okay, so now if you expand this, you will get this 2 into 10 power minus 7 ln 1 by r1 dash plus 2 into 10 power minus 7 ln d by 1. Okay, this is in henries per meter. If you convert that into ln to logarithmic terms and henries per meter into millihenries per kilometer, you will get this equation. Okay, similarly, if you write for conductor 2, the inductance equation is L2 is equal to 2 into 10 power minus 7 ln d by r2 dash. Okay, so now here also this you can write it this ln d by r2 dash we can write it as ln 1 by r2 dash plus ln d by 1, like that. Okay, so then L2 you can write it as 2 into 10 power minus 7. If you expand this, 2 into 10 power minus 7 ln 1 by r2 dash plus ln d you will get. So 2 into 10 power minus 7 ln d. So this equation you will get. So here you have the 2. So similarly, if you convert ln into logarithmic term and henries per meter into millihenries per kilometer, you will get this equation. Okay, so now if you observe these equations here, so this inductance L1 and inductance L2 is divided into two parts. This is first part and this is the second part, right? So here, so if both the conductors are identical, so that means if the radius of two conductors are the same, so then as you know the value of inductance will be same. L1 will be equal to L2. So let us assume this value will be equal to L here. Okay, in such a case you can write the inductance equation will be finally this value, right? So that value is 0.4605 log 1 by r1 r dash plus 0.4605 log d by 1. So which is in millihenries per kilometer, right? So if it is in henries per kilometer, the value will be L is equal to 2 into 10 power minus 7 ln 1 by r dash plus 2 into 10 power minus 7 ln d by 1 you will get. Okay, so this is in henries per meter. Okay, so whatever may be the case, whether it is millihenries per kilometer or henries per meter, so if you observe both the equations, so both the equations are having the two terms. Okay, so first term is 2 into 10 power minus 7 ln 1 by r dash, and second term is 2 into 10 power minus 7 ln t by 1, right? So if you observe these two terms here, the first term in this equation is depending upon the r dash, right? So r dash is, you can call it as a fictitious radius, and this r dash value you already know, so which is 0.7788 times the r. Okay, so this r dash you can call it as geometric mean radius, or you can also call it as this is a fictitious radius of the conductor. Why? Because the actual radius of the conductor is r here. Okay, so but we are consider this r dash is the 0.7788 times the r. Okay, so this r dash you can consider to be a fictitious radius. Okay, the first term depends upon the only r dash, right? So only r dash in the sense this first term depends upon the radius of the conductor only. Okay, so but if you see the second term here, okay, so the second term depends upon the capital D. So what do you mean by capital D? So capital D is the distance or spacing between the two conductors. Okay, so the second term depends upon only the spacing between the two conductors. Now this second term is called the inductance spacing factor or inductive reactance spacing factor. Okay, second term in the above equation. So from this equation only you can determine the factor which decides the spacing between the two conductors, right? So this second term depends upon only the distance or spacing between the two conductors. So this second term is called the inductance spacing factor or inductive reactance spacing factor. So if you are asked to find out the inductive reactance spacing factor, so you need to take this 2 into 10 power minus 7 ln d. Okay, so 2 into 10 power minus 7 ln capital D, so will be your inductance spacing factor. Okay, or this also can be called as inductive reactance spacing factor. Okay, right. Let us see one numerical problem here. So the problem is a 60 Hz single phase 2-wire overhead transmission line has solid cylindrical copper conductors with a 1.5 centimeter diameter. Okay, so here you have a 2-wire single phase transmission line, and the frequency is given as 50 Hz, and diameter of the conductors it is given as 1.5 centimeter. So once you know the diameter, you can calculate the radius. That radius is diameter by 2, so which will be equal to 1.5 by 2, so which is 0.75 centimeters. Okay, so they also given that the conductors are arranged in a horizontal configuration. Okay, two conductors are arranged on a horizontal configuration, and the spacing between the conductors is given here as 0.5 meters. So that means from centers to centers the spacing is given as 0.5 meters, so not centimeters, 0.5 meters it was given. Okay, so this is nothing but capital D. So the capital D value is given, which is 0.5 meters. Okay, so now you can convert this meters into centimeters, so that 0.5 into 10 square centimeters you will get. Okay, so which is nothing but 50 centimeters. Okay, so capital D, which is the distance between the two conductors, or you can even call it as the spacing between the two conductors. Okay, so this is given, which is 50 centimeter. Now you have to calculate in millihenries per kilometer the inductance of each conductor due to internal flux linkages only, right? So you have to consider only the internal flux linkages and you have to determine the inductance of each conductor, okay, due to these internal flux linkages, okay. And also you have to determine the inductance of each conductor due to both internal and external flux linkages. So in the second time you have to determine the inductance of each conductor by considering the both internal flux as well as the external flux linkages, right? So then in third case you have to find the total inductance of the transmission line, okay. So you have to first bit is you have to find the inductance of each conductor, right? So by considering only internal flux linkages. In the second bit you have to calculate the inductance of each conductor by considering both internal flux as well as the external flux. And in the third bit you need to find out the total inductance of the single phase two-way transmission line, okay. So let us solve this. So given here a diameter is 1.5 centimeter, 1 centimeter. So the radius will be 0.75 centimeters, right? So here the radius is 0.75. So here it is wrongly mentioned. So it is D actually, okay. So this is D. So D is equal to 1.5 centimeter. So from this you calculated the R, which is 0.75 centimeter, okay. And capital D spacing between the conductor is given as 0.5 meters. If you convert this into centimeters you will get 50 centimeters, okay. So now you have to calculate the first bit, A bit, okay. So A bit is you have to find out the internal inductance of each conductor by considering only the internal flux linkages, okay. If you consider the only internal flux linkages, you know the inductance formula. So L inter, so which is nothing but inductance by considering only internal flux linkages. So this value will be equal to 1 by 2 into 10 power minus 7 henries per meter, okay. This formula we are going to take, okay. So this will be equal to 1 by 2 into 10 power 9 minus 7, so which is in henries per meter, okay. So but if you see the problem, you have to calculate these inductances in millihenries per kilometer. So you have to convert this henries per meter into millihenries per kilometer. So that means henries, if you consider henries, 1 henry will be equal to 1000 millihenries, right? So you can write this here. If you can multiply this total value with 1000 millihenries by 1 henry, so that it will be converted into millihenries. Now if you want to convert meters into kilometers, how you can do? 1 meter is equal to 1 by 1000 kilometers, okay. So 1 by 1000 kilometers. So now you can write it as 1 by 1 meter is equal to 1000 kilometers, okay. So now here you have 1 by m, so 1 by meters. So in place of 1 by m you can write this 1000 kilometers, right here. So this product, okay. So that you will get the total value in millihenries per kilometer. So now the value will be 0.05 millihenries per kilometer, okay. So this is for each conductor. So for each conductor the value will be the same, okay. Why? Because the radius of each conductor will be the same, okay. So this is about the internal flux linkages. Now you need to calculate the inductance of each conductor due to both internal flux as well as external flux, right? This is A bit. Then B bit, you have to consider the two conductors as X and Y. Now the inductance of first conductor X will be Lx, inductance of second conductor will be Ly. As the diameter is same for both the conductors, the inductance also will be the same, okay. Lx will be equal to the Ly. So on the formula for calculating the inductance is 2 into 10 power minus 7 ln capital D by R dash, okay. So now here you substitute the values, 2 into 10 power minus 7 ln, what is the value of capital D? So capital D is 50 centimeters, 50 by, what is R dash here? So R dash is nothing but 0.7788 times R, right? So R here is 0.7788 0.75 centimeter. Okay, now if you calculate the total value, you will get in henries per meter. Okay, so now this henries per meter you can convert into millihenries per kilometer simply by multiplying this total value into 10 power 6. Okay, so if you multiply this total value with the 10 power 6, you will get the value in millihenries per kilometer. Okay, so if you are confusing with this all this, so then you simply multiply this total with the 10 power minus 6 so that the value will be converted into millihenries per kilometer. Okay, so the final value for the inductance of each conductor will be equal to 0.8899 millihenries per kilometer for each conductor. Okay, so once you know the inductance of conductor 1 and conductor 2 by considering both internal flux as well as external flux, then you can determine the total inductance. The total inductance of the single phase circuit will be sum of the inductance of two conductors, right? So L is equal to Lx plus Ly. So the value for total inductance will be 2 times of this 0.8899. So then the value will get 1.780 millihenries per kilometer. Okay, so this is the total inductance of your single phase line. So this inductance you can also call it as a loop inductance. Okay, so let us see another problem. Okay, so in this problem you have to rework problem 1 if the diameter of the each conductor is increased by 20%, so which is nothing but to 1.8 centimeter. Okay, or decreased by 20% to 1.2 centimeter without changing the phase spacing. Okay, so you have to consider the same problem, okay, which is given in the problem 1. Okay, the description problem 1 will be the same. Okay, it is a 60 Hz single phase 2-way overhead transmission line with a solid cylindrical copper conductors with a diameter. Here it is 1.5 centimeter diameter is given. Okay, so now here in the second problem you have to increase the diameter of each conductor by 20%, right? So in problem 1, so diameter D is given as 1.5 centimeter. Okay, so if you increase the diameter to 20%, then the diameter will become 1.8 centimeter. Okay, so increasing 20% means you have to multiply this diameter 1.5 into 20%. So 20 by so 1.2 you have to multiply. So if you multiply with 1.2, you will get 1.8 centimeter. Okay, so that value is directly given here in the problem itself, right? So when the diameter of conductor is increased to 20%, it will become 1.8 centimeter. Now by considering 1.8 centimeter diameter, you have to rework the problem. Okay, that means you have to determine again all these three. So inductance of each conductor due to internal flux alone, the inductance of each conductor due to both internal flux as well as external flux linkages, and the total inductance. Okay, so just they are changing only the diameter. Okay, diameter is increased to 20%. So in similar way, in the second bit, if the same diameter is decreased by 20%, so that means 1.5 centimeters, which is in problem 1, so this is decreased to 20%. It means so this 1.5 is multiplied with 0.8, so that you will get 1.2 centimeter, right? So this is also given in the problem itself. Okay, so if the diameter is decreased to 20%, which is 1.2 centimeter, then how will be the value of inductance for the each conductor when you consider the internal flux linkages only, and what is the inductance of each conductor if you consider the both internal flux as well as external flux linkages, and what is the total inductance of the line. So you have to determine this. So let us see the first case. Okay, so in the first case your diameter is increased by 20%, so the diameter D will become, so here the diameter D will become now it will be equal to 1.8 centimeters. Okay, so 1.8 centimeters in the sense if you want a radius, R will be 1.8 by 2, so this will be 0.9 centimeter is the radius. Okay, and spacing between the two conductors will be not changing. So that's capital D will be 0.5 meters only. So this value, if you convert into centimeters, you will get 50 centimeters. Okay, so now you calculate the internal inductance. Okay, so internal inductance equation is L int will be equal to 1 by 2 into 10 power minus 7 henries per meter. Okay, so the equation will be the same, right? So this value is equal to 1 by 2 into 10 power minus 7. Now you have to convert this henries per meter into millihenries per kilometer, right? So if you convert henries to millihenries, what you will get? 1000 millihenries by, so meters into kilometers if you convert, so then what you will get? 1 by 1000 or 10 power minus 3 kilometers you will get. Okay, so which is nothing but 1 by 2 into 10 power minus 7 into 10 power 6 millihenries per kilometer. Okay, so for converting henries per meter into millihenries per kilometer, if you just have to multiply with the 10 power 6 only. Okay, so then what you will get? This will be equal to 1 by 2 into 10 power minus 7 into 10 power 6. You will get 10 power minus 1 here. Okay, so this 1 by 2 is 0.5. So 0.5 and 10 power minus 1 is nothing but by 10 you can consider. So this value will be 0.05 millihenries per kilometer. Okay, so internal flux linkages. So if you consider the inductance due to internal flux linkages alone will be L int is equal to 1 by 2 into 10 power minus 7 henries per meter. And if you convert that henries per meter into millihenries per kilometer, so then that L int value you are getting it to be equal to 0.05. So 0.05 millihenries per kilometer for each conductor. Okay, so this is for first one. So then you have to determine the inductance of each conductor by considering both internal as well as external flux linkages. When you consider both internal as well as external flux linkages, the formula for determining the inductance is 2 into 10 power minus 7 ln d by r dash, right? So capital D here is the distance or spacing between the conductors, and r dash value is nothing but this value 0.7788 times r, right? So now the inductance for both the conductors in a single phase system will be same. Lx is equal to Ly. So why? Because the diameter will be the same for the both the conductors. Okay, so this value is equal to 2 into 10 power minus 7 ln d by r dash here. Okay, so now you substitute the values here, 2 into 10 power minus 7 ln. So d here is nothing but 0.5 meters. Okay, or you can directly consider it to be 50 centimeter. Okay, so you can write this. This will be equal to 2 into 10 power minus 7 ln d is 50 centimeters by r dash here is nothing but 0.7788 times r. R value is 0.9. Okay, so now once you calculate this, you will get the value in henries per meter. Okay, now you have to convert this henries per meter into millihenries per kilometer. So you have to just simply multiply with 10 power 6. Okay, so once you multiply this with the 10 power 6, then the value you are getting here is millihenries per kilometer. So the value of inductance for each conductor by considering both internal flux as well as external flux, the inductance value you are getting it to be 0.8535 millihenries per kilometer for each conductor. Okay, so on the total inductance value L will be equal to sum of the two inductances, so which is Lx plus Ly, which is nothing but 2 times of this value. Okay, so you are getting the total inductance will be equal to 1.707 millihenries per kilometer. Okay, so this is called the total inductance or loop inductance of single phase line. Okay, then the second bit is if the diameter is decreased to 20%, so that means diameter D is equal to 1.2 centimeter. So how will be the internal inductance by considering internal flux alone, and what will be the inductance of each conductor by considering both internal as well as external fluxes? Then what is the total inductance of the circuit? You have to determine. Okay, so D here is 1.2 centimeters. Okay, and capital D is spacing between the conductor, it is fixed, which is 0.5 meters. So 0.5 meters in the sense this is 50 centimeters, and the diameter if you convert into radius r will be equal to diameter by 2, so that you will getting 0.6 centimeter. Okay, r is 0.6 centimeters and capital D is 50 centimeter. Now the formula for calculating the inductance in Henrys per meter will be L int is equal to 1 by 2 into 10 power minus 7 Henrys per meter. Now if you want to convert this into millihenries per kilometer, simply you have to multiply this 1 by 2 into 10 power minus 7 with the 10 power 6. Okay, so that the units will become millihenries per kilometer. So then you calculate this value, you will get 0.05 millihenries per kilometer. Okay, so this value. Right. So then inductance of each conductor. So by considering both internal flux as well as external flux. So the formula for calculating the inductance will be 2 into 10 power minus 7 ln d by r dash. Right. Now in this formula, if you substitute the values, then 2 into 10 power minus 7 ln d here is 50 centimeter and r dash is nothing but 0.7788 times the r value, and r value here is 0.6. Okay, so this value is in Henrys per meter. Okay, so now if you multiply this total value 2 into 10 power minus 7 ln 50 by 0.7788 times the 0.6 with the 10 power 6 here, if you multiply this total value with 10 power 6, then the units will be converted into millihenries per kilometer. Okay, so now you calculate this value with your calculator, so that you will get the value of inductance will be equal to 0.9346 millihenries per kilometer. So this is the value of inductance per each conductor. Okay, now if you want the total inductance of your circuit, so the total inductance of your circuit L will be equal to Lx plus Ly, so sum of two inductances. Okay, so then this value will be equal to 1.869 millihenries per kilometer you will get. Okay, so this is how you can get the total inductance of the circuit. Okay, so now if you consider all the three cases, right? So problem 1, if you see, so in problem 1, if you go here, so internal inductance is 0.05 millihenries per kilometer, and each inductance of conductor is 0.8899 millihenries per kilometer, and total inductance is 1.780 millihenries per kilometer. That those values we are writing here. Okay, L internal, Lx and Ly values, and total inductance L value in problem 1. And in problem 2, case 1 is, so diameter is increased to 20%, right? So then in such a case, if you find the internal inductance value, so what are the values you are getting here? So here you are getting the internal inductance to be 0.05, and inductance of each conductor by considering both fluxes to be 0.8535, and total inductance is 1.707. So those we are going to write here. So 0.05, 0.8535, 1.707. Okay. So in the second case, in problem 2, so which is decreasing the diameter of the conductor to 20%. So then in such a case, you are getting the internal inductance will be 0.05 millihenries per kilometer, and the inductance of each conductor by considering both the fluxes will be 0.9346 millihenries per kilometer, and the inductance L is equal to 1.869 millihenries per kilometer. Those we are writing here. Internal inductance 0.05 millihenries per kilometer, and Lx and Ly by considering two fluxes will be 0.9346 millihenries per kilometer, and L is 1.869 centimeters. Right? We are making a table for all the values here. Okay. Now if you observe these values, okay, the internal flux linkages, if you consider only, the inductance due to internal flux linkages in all the cases will be the same. Right? Internal inductance in all the cases it will be the same. Why? Because the internal inductance, this value will be 1 by 2 into 10 power minus 7, so Henrys per meter. Right? So this value does not depend upon the radius of your conductors. Right? So when you change the radius, whether you decrease or increase, the value of internal inductance doesn't change. Okay, in all the cases you will get the same value. So, but if you observe the inductance of each conductor as well as total inductance L. If you observe both the two, right? So this is in problem 1, in problem 1 and in problem 2 for the first case. So first case is nothing but here increasing the diameter to 20%, right? When you increase the diameter of the conductor to 20%, so then you can observe that the inductance of each conductor as well as the total inductance, both are decreasing. Okay, so both are decreasing. Okay, so now if you see here, 0.8535 is the inductance of each conductor when diameter is increased to 20%. Okay, before increasing, the value is 0.8899 value. Now if you find this ratio, you will get the, so what is the value once you find that ratio? So I will tell you 1 minute. So 0.8534 by 0.8899. So if you calculate this value, you are getting 0.9589. Okay, you are getting 0.9589. So that means the value of inductance decreased by increasing the conductor diameter 20% is 4.1%. Okay, so this in percentage, if you write 95.9%, you can write. Okay, so that decrease in inductance value will be 4.1%. Okay, so because of increase in the diameter of the conductor, the inductance value will be decreasing here. Okay, so if you observe the total inductance also, you will get the decrease zone. So here you are having 1.780, here you are having 1.707. So here the total inductance also will be decreased by the same percent, 4.1%. Okay, now if you observe the second case in problem 2, okay, so the inductance of each conductor, if you observe with the first case, problem 1, okay, so because of decreasing the conductor diameter, your inductance of each conductor is going to be increased from 0.8899 to 0.9346, and also the total inductance also will be increasing. Here before increasing it is 1.70 millihenries per kilometer before decreasing, so right. So then after decreasing the diameter to 20%, you are getting the inductance to be increased. The value you are getting it to be 1.869 millihenries per kilometer. Now how much value it is increased? So if you want to know, so then in such a case, what you have to do, you divide this total value with this value, right? 1.869 if you divide with 1.780, so then you will get some value. So what value you will get? 1.869 if you divide with 1.780, so then you are getting this value will be equal to 1.05. Okay, so 1.05, if you convert this into percentage, you will get 105%. Okay, that means 5% increase will be there in the inductance if you decrease the diameter of the conductor. Okay, so with this example, you can conclude that if the diameter of the conductor is increased, then the value of inductance will be decreased. If the diameter of the conductor is decreased, then inductance value will increase. So this is the conclusion. So let us see another problem here. So find the inductive reactance spacing factor for a 60H single phase 2-wire line with the conductors arranged in horizontal configuration with 2 meter spacing. Okay, so here you have a single phase line with 2 conductors, and spacing between the 2 conductors it is given to be 2 meters. Okay, that means capital D is equal to 2 meters here. Okay, then you need to find out the inductive reactance spacing factor, right? So inductive reactance spacing factor, the formula is 0.4605 into log D, or you can even take it as 2 into 10 power minus 7 log D. Both are the same. Okay, so if you go here, okay, the second term in this expression is your inductive reactance spacing factor. If you consider the first one, so this value will be 0.4605 log D you will get, And if you consider the second equation, you will get the inductive reaction spacing factor will be equal to 2 into 10 power minus 7 log D. Okay. So here they are taking 0.4605 in terms of log D. So in such a case, D value is given. So D value is given here to be 2 meters. So if you substitute here, then you will get 0.4605 into log 2. So then the value of inductive reactance spacing factor is 0.1386. Like that, you can calculate the inductive reactance spacing factor of a transmission line. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.